Swayam Prabha. Digital India. Educated India.
Welcome to the fifth lesson on module 2, which is on analysis of strain, part 5. Now, in the last lesson we had discussed certain aspects of strain which are caused due to the change in the temperature. Now, in this particular lesson we are going to look into some more aspects of strain which are caused due to change in temperature, especially in bars or assembly which are made out of different material. Also, we will look into certain aspects of misfit or lack of fit. Well, once this particular lesson is completed, it is expected that one should be able to understand the concept of strain due to change in temperature in compound bars. Also, one should be able to understand the concept of misfit, which we call occasionally as lack of fit, and pre-strains and thereby the pre-stresses, and which are basically indeterminate system, and we will look into the aspects on these. Hence, the scope of this particular lesson includes the recapitulation of previous lesson, and as we have seen earlier, we generally discuss the questions which have been posed last time, and through that we will recapitulate the aspects which we have discussed in the previous lesson. Evaluation of strain in compound bars due to variation in temperature, then the concept of misfit and the pre-strain and thereby the pre-stresses, evaluation of stresses due to change in temperature in different systems and also due to pre-strain in the systems. Well, let us look into the answers of the questions which I had posed last time. The first question which was posed is what are the steps for the evaluation of unknown forces for indeterminate systems. Now, if you remember, last time we had differentiated between the determinate system and the indeterminate systems, and we had categorized that what are the steps that are necessary for carrying out or evaluating the unknown forces for indeterminate systems. Now, let us look into the steps that are necessary. Number 1 is the equilibrium equation or the equilibrium conditions, and these conditions or the equilibrium equations can be written down if we draw the free body diagram of the system given. And as we have seen, when we had solved several problems, we had taken the free body of the whole system, and then from the free body diagram of the system we can write down the equations of equilibrium, which says that summation of horizontal forces as 0, summation of vertical forces as 0, and the moment with respect to a point is equals to 0 in the system, and that gives us the equilibrium criteria. Secondly, the second step which are necessary for the solution of, now if the system is statically determinate, then from the equations of equilibrium we can solve the system, but if the system is indeterminate, then we need to solve or we need to write down the geometric compatibility, and which gives rise to the compatibility equation, and this compatibility equation can be arrived at if we draw an exaggerated sketch of the deformation pattern. As we have seen through several examples, that though the deformation is small, when we had drawn the exaggerated view of the deformation, it becomes clearer that how the system is deforming, and it becomes easier to write down the conditions thereby, which we call as the compatibility condition, and which leads to the compatibility equation. Now, once we write down the equations of equilibrium, equations of compatibility, and then with the help of the constitutive relationship, which gives us the relation between the strain and the stress, and thereby stress we can write down in terms of the forces. So, we have equations of equilibrium written down in terms of the forces, we have the equations of compatibility written down in terms of forces through the Hooke's law or the equations of constitutive relationship. So, once we have these two sets of equations, we can solve for unknown forces. So, the solution of equilibrium and compatibility equations are utilized for the solution of unknown forces. So, these are the steps that are necessary for the solution of indeterminate problem. Now, the second question which was posed was that what is the expression for thermal stress. Now, before we evaluate the expression for thermal stress, let us look into the definition of thermal stress. Now, as we had defined last time, the total or partial restriction of deformation induces internal forces, and which resist forces due to thermal expansion, and these stresses caused by these internal forces are termed as thermal stresses. And if you remember, as I said, that if you take a body and if this is allowed to undergo change in temperature, if it is not restricted or constrained, it will move or expand if the temperature rises. But then if we do not allow this body to move freely, if we put some restrictions, then the expansion will be restricted, and thereby the internal force will be induced into the system. Now, the stresses that is induced because of these forces, which is being caused due to the expansion, the thermal expansion, or due to the change in the temperature, we call that as thermal stress. So, to evaluate the value of the thermal stress, let us look into the expression which we had derived for the strain, or which we had written down for the strain. Now, strain due to variation in temperature, which is delta T, the final temperature minus the initial temperature, is given as epsilon T is equals to alpha times delta T. Now, if the deformation due to temperature is written as delta T, this is equals to epsilon T times the length of the member as L, and epsilon T is equals to alpha times delta T. So, this is alpha times delta T times L. So, this is the deformation of the member. Now, when the body is allowed to move freely, that means it is undergoing expansion due to rise in temperature, and we call that expansion as delta T. Now, if we do not allow this expansion to happen in this member, that means we are putting some restriction. So, thereby we are imposing some force into it, which will bring back this deformation to its original position. And because of that, this deformation delta T should be equals to the deformation that is being generated because of the applied force, which is equals to P times L divided by AE. So, PL by AE is equals to alpha times delta T times L. Now, the parameter P by A, the force divided by the cross sectional area, we can write that as stress. So, stress sigma is equals to E times alpha times delta T times L divided by L, and this L gets cancelled out. So, the stress is equals to E times alpha times delta T. So, the stress sigma T due to the change in the temperature is equals to E times epsilon T or E times alpha times delta T, where E is the modulus of elasticity of the material, alpha is the coefficient of thermal expansion, and delta T is the change in temperature. So, this is the expression for the stress due to the thermal effect or thermal stress. Let us look into the last question which we had posed. Is the evaluation of thermal stress in a stressed body or determinate one? Now, from the discussions that is going on for last few sessions, probably you should be able to answer this question, as we have said that the variation of the temperature is basically is not possible to solve using equations of equilibrium, and hence they are not statically determinate. So, forces developed due to temperature changes cannot be determined from equilibrium equations only, and thereby these particular kind of systems are statically indeterminate, or where there is a change in the temperature in the system, when we evaluate the forces because of that, or when we evaluate the thermal stresses due to change in temperature, the system is statically indeterminate, and we need the help of compatibility equations, so that we can solve the stresses due to temperature change. Well, having looked into the questions, let us look into what will be the effect of change in temperature, or what is the effect of thermal stress in compound bars. Now, compound bars are the ones where we have a system made out of materials of different types, thereby their thermal expansions or contraction, they are of different magnitudes. Now, if we look into a system which is quite common, it is like a bolt which is put into a sleeve, and this is the bolt head. Let us say this particular part is the outer sleeve, and this is the bolt which has a threaded part here. This is the bolt head, and this assembly, this is the washer plate which is provided at the end. So, the whole assembly is allowed to undergo a change due to temperature. Let us say there is a rise in the temperature, the whole system undergoes change in temperature, and let us assume that the thermal expansion for the outer sleeve is larger than the central bolt. So, if we say the coefficient of thermal expansion for the sleeve as alpha s, so alpha s is greater than the coefficient of thermal expansion for the bolt, which is alpha b. Now, when this whole system is undergoing a change in the temperature, now to look into that how much stresses that are getting generated in the system because in the change in the temperature, let us proceed step by step. First, we remove the head of the bolt and allow the sleeve and the bolt to expand freely because of the change in the temperature. So, in the second figure as it is shown, we have removed the bolt head and allowed the whole system to expand freely. Now, as a result, since the thermal expansion coefficient of the outer sleeve is larger than the bolt inside, so it is expected that the outer sleeve will undergo more expansion than the central bolt, and since it is free to move, it has expanded. Let us say that the expansion of the sleeve from its original position is equals to delta 1. This was the original position and it has moved to this particular position. So, the distance that it is moving is delta 1, which is due to the change in the temperature, which is given as alpha s times delta T, which is the change in temperature final minus the initial temperature multiplied by the initial length L. So, alpha s times delta T times L is the expansion of the sleeve. Consequently, the bolt also will undergo expansion, but since the thermal expansion coefficient is less than the outer slip, it will have relatively lower value than delta 1, and let us say that this was the original position of the central bolt, and this is the position which has been reached after the thermal expansion, and let us call that as delta 2. So, delta 2 is equals to alpha v times delta t, that is the strain in the central bolt, multiplied by the length L. Now, when they are not constrained or not restricted, they are freely expanding and having expansion or the deformations delta 1 and delta 2. But since the bolt head is present, it is not allowing it to move freely. As a result, there will be forces generated and thereby stresses generated. Now, the force in the central bolt and the outer slip will be such, the central bolt and the outer slip should be such that they come to a common position. So, thereby the central bolt will have a tensile pull and the outer slip will have a compressive force. These two forces are equal. In fact, these and this in a combined form will be equals to this. So, in effect, if I impose these two forces, their effect is 0. So, this is being pulled and this is being compressed. So, as a result, they will come to a common position, which will be the stressed position for the whole system. So, it has expanded freely by delta 1, the outer slip. Now, because of the compressive force that is getting applied on the outer slip, this will come back to the position from this position to the final position here. The third figure indicates the final position of the outer slip and the central bolt, where both are in the same line having the same deformation. Now, to bring back to this particular position from the free expansion of the outer slip, this much is the deformation that is required to be brought back by application of this compressive force. Let us call that as the slip force PS. This to combine is the PS. So, if we call this as delta 3 is equals to PS LS, which is L of course, divided by cross sectional area of the slip times E of the slip. So, this is the amount of deformation that will be generated in the slip because of the application of this force PS. Now, to bring to this particular position to the central bolt, we need to apply a tensile pull, so that is elongated by this much of amount. Now, this is the position after thermal expansion, and this is the position where we need to bring this bolt in. So, this is the amount of deformation that is undergoing in the bolt, which is equals to delta 4, and delta 4 thereby is equals to P bolt, if we call this as P bolt, the central one, PB times L by A bolt times E bolt. So, these are the 4 deformations that at different stages these members are undergoing. And the final deformation, this is the final form from its original length. So, this is the final deformation, which is equals to delta. So, thereby delta is equals to, delta will be equals to, delta was the free movement of the slip because of the temperature, and it has been brought back to the final shape by application of the force PS, which is delta 3. So, delta 1 minus delta 3 is the final position delta for the outer slip, and for the central bolt, the free thermal expansion was delta 2. From its initial position, it has expanded to delta 2. Now, to bring this to the final position of the combined system, it has to be expanded further by application of this tensile pull PB, which is delta 4. So, this is equals to delta 2 plus delta 4. So, the final deformation in the whole system, whole assembly of the compound bar, this is equals to delta. So, the final deformation delta is equals to delta 1 minus delta 3 or delta 2 plus delta 4. So, we can write the compatibility equation now as delta 1 minus delta 3 is equals to delta 2 plus delta 4. Now, in addition to this, we need to have the equation of equilibrium. Now, for this particular system, if you look into the equation of equilibrium, there that the forces which are being applied to bring back to its final form, which is Pb is equals to the force in the slip Ps. So, this is the equation of equilibrium number 2 and this is the equation of compatibility number 1. So, we have now two equations. Now, this particular equation is written in terms of forces. Now, if we substitute the values of delta 1, delta 3, delta 2 and delta 4, we write down them in terms of forces and alpha 1, alpha b and alpha s. Finally, we can write down the expression for using these two equations Pb equals to Ps and the expression for deltas which we can convert in terms of forces. We can evaluate the values of Pb and Ps. So, we can evaluate values of Pb and Ps which are in terms of alpha, delta t, the length and of course, the cross sectional area of the members and the modulus of elasticity of the material that is being used. So, once we know the values of Pb and Ps, we can compute the stresses in the member, we can compute the final value of delta which is equals to delta 1 minus delta 3 or delta 2 plus delta 4, which will give the value of delta which is the final deformation in the whole assembly. So, from the values of Pb and Ps, we can calculate the values of stresses which are sigma b and sigma s. Sigma b is therefore equals to Pb divided by the cross sectional area of the bolt and sigma s, the stress in the slip, sigma s is equals to Ps divided by cross sectional area of the slip. So, in the process we can compute the values of the stresses and also we can evaluate the value of the deformation delta for such compound system. Now, let us look into another term which we call as misfit or another term which we call as pre-strain. Now, many a times we get structural system which are consisting of several members. Now, it may so happen that any of the members of the whole structural assembly are not to the exact length as it should be, either it is longer or it is shorter. Now, if that happens, then when we try to assemble the whole structural system using these individual members, the length which is shorter or longer causes some problem in the assembly, and this is what is termed as misfit. It is not fitting appropriately in the system, and that is why this particular term misfit comes in. Now, if the structural system is a determinate one, let us take an example. Let us say we have one bar which is pinned at this end, and this bar is connected by another bar and connected at this position. Now, let us assume that this, let us say this is AB and this is CD. Now, if this particular member of the structure CD, if it is not exactly to the length as it should be, let us call this length as L. If this particular member is having some defect and the length is not perfectly L, either smaller or larger, then eventually this member is not going to fit in the whole structural system, and this we generally designate as misfit. Now, many times of course, this misfit is introduced in the system intentionally. Now, many times it is required to have a system where we like to introduce some kind of strain beforehand. Now, when we introduce this misfit in the system, thereby we try to introduce some amount of strain before really it is loaded and thereby subjected to strains. So, when we form such systems or when we form such structural system where we introduce the strain beforehand, we call that particular system as pre-strained system, and thereby from the strain the stresses can be evaluated, and we call those kind of systems as pre-stress system. One of the example which is very common, which we look very frequently, is the spokes in a bicycle wheel, where the spokes are in fact strained beforehand, so that the whole wheel remains in position. If they are in loose form, it will collapse. Now, coming back to this example, now when this particular system is a determinate one, as is the case in this particular example, this misfit is not going to cause as such any problem to the structural system. Means that if this particular member CD is longer, then what at best can happen is the bar AB may have some geometric imperfection in terms of rotation. So, it may not look straight as it should be, or if the length is shorter than L, then it might so happen that the horizontal bar will no longer remain horizontal, but it may rotate to certain extent. But in the process, what is going to happen is that the whole structural system will not be subjected to any kind of strain or stresses. On the contrary, if we look into a system, or if we look for structural system which is indeterminate, and if we have any member which is shorter or longer than its actual length, then that induces strains or the stresses in the system. So, if we consider an example where the system is an indeterminate one, then let's look into that. Say we have again a bar which is connected at this point, and let us say we have two bars connected at this point and connected at this point. Now, let us say this is A, this is B, this is C, this is D, this is E, this is F. Now, let us assume that the length of both bars CD and EF are L. Now, if one of these bars, let us say CD, is longer than the length L, then there will be problem that we cannot fit in the member CD in the whole structural assembly. As a result, what is going to happen is that, or what if we like to fit in that longer bar in the whole system, what we need to do is that we stretch this whole assembly, fit in the bar CD in its position and place them in position and release this force. So, as a result, what is going to happen is the whole of assembly, the bar EF, bar AB, they will be subjected to some amount of strain, and there will be stresses induced in the bar. So, if the system is indeterminate one, if we have length of the member not exactly as we desire, then there is a possibility that the structural system will be subjected to some amount of strain, and these strain or the stresses are pre-introduced in the system before the system is loaded or any loads are applied on that system, and this is what we call as pre-strains or pre-stressing. And many times we introduce this kind of pre-straining or pre-stressing in the system intentionally to avoid some problem in some situations, which we will look into at a later stage. Well, then if we have this kind of misfits or the pre-strains, then what are the consequences of that? Let us look into. Now, the simplest way to introduce these pre-strains or the pre-stressing in the system is the use of the bolts. Now, many times we encounter this kind of bolting system or the nut bolt system, which is shown here. So, this is a bolt having the nut here, and this is the bolt head. Now, when this nut is rotated, if we start from one point and rotate it to one complete round, the nut moves forward. The nut moves forward, and this movement is over a length in the threaded part of it, which we commonly term as pitch. So, if we look into that threaded part, which we have in this form, now when the nut is rotated, along the threaded part, the nut moves ahead, and when it moves from one point to the other by giving a complete 360-degree rotation, it moves ahead over these two peaks, which we designate as the value P, which we call as pitch. So, if there are n number of turns, if we turn the nut by n, then the total movement of the nut, if we call that as delta is going to be equals to n times the pitch P. Another system which many a times are used are known as turnbuckle. In the turnbuckle, what happens, the threaded part are introduced on either side, and this particular system, which is a turnbuckle, which once it is rotated, both the threaded part moves. Once the turnbuckle, the central part is rotated, since we have threads on either side, both sides move forward or backwards by one pitch. So, if we have one complete turn of the turnbuckle, then we have two movements, which is equals to 2 times P. So, if we rotate the turnbuckle n times, then the total movement which we expect of the threaded part is equals to twice n times P. So, in case of turnbuckle, the deformation delta of the central part or the threaded part, we can call it as equals to twice n times P. Now, this misfit or many a time some deformation are introduced in the system by using the turnbuckle, and we introduce some amount of pre-straining or pre-stressing in the member. Now, if we have this kind of pre-straining in the system, then the evaluation of the effect of such pre-straining or the evaluation of the stresses are exactly same as that of the effect due to temperature change. So, the way we have analyzed a system for thermal stresses due to change in temperature, we carry out exactly similar steps to evaluate the effect of such pre-straining system, or in other words, we write down the equations of compatibility and equation of equilibrium, and then we relate the strain to the stresses through constitutive relationship, and we evaluate the unknown forces and thereby the stresses that is introduced in the assembly. Now, let us look into that. If we introduce this kind of pre-straining, then how do we get the stresses in the system? Let us say we have an assembly where we have a central shaft which is made out of copper, and we have two steel wires on two sides where two turnbuckles are introduced. So, this is the turnbuckle, and this is also the turnbuckle. Now, in the first instant, as we have done in the case of thermal analysis, in the case of the evaluation of the stresses because of the change in the temperature, we go exactly in the similar steps to evaluate the stresses due to such pre-straining. Now, we remove this head, which is the rigid head or rigid plate. Now, if we remove that and let us say we introduce n number of turns in the turnbuckle, in both the turnbuckle are turned n times, so that there is a shortening of the bar, that means the threads move inside. So, since the pitch as we have defined as P, because of the turning of one revolution of the turnbuckle, so both the threads are moving by twice P. So, n number of turns are there. So, total deformation is equals to 2 np. So, let us call that this deformation which we introduce is equals to delta 1, which is equals to twice np. Now, this is the original position of the central copper bar. Now, if we like to look for a system wherein we will pull this slip or the steel wire to a position and compress this central copper to a position where they will come to a common position, then the steel wire will be extended because of the pull, and because of the compressive force the copper bar will be compressed. So, the final deformation should be the same in both, and that final deformation, now because of the tensile pull that we are going to apply on the steel wire, let us say from this position to this position, when it comes, if we call that as delta 2, this is equals to, if we call the force in the steel bar as Ps, as Ps times L by A E or A steel E steel. So, this is the deformation that is occurring in the steel bar because of the application of the force Ps. Now, the compressive force which is being applied into the copper bar, if we call that as Pc, so the deformation which is from this position to this position, which we call as delta 3, this delta 3 is equals to Pc times L by Ac times Ec, or Lc and Ls, let us call it. So, then the final form is, which is from original length to this particular length, which is equals to delta, and this delta is nothing but equals to, which is delta 3 is equals to delta 1 minus delta 2. So, we can write the condition that delta 1 minus delta 2 is equals to delta 3. So, this is the compatibility criteria which is occurring because of the application of the pre-straining in the system. Also, the equilibrium equations, if we write, if we look into that, we have two steel wires which are being pulled by a force Ps, and we have the central copper bar which is being compressed using the force Pc. So, in equilibrium situation, Pc should be equals to twice Ps. So, we have the equation of compatibility, which is delta 1 minus delta 2 equals to delta 3, which can be written in terms of Ps Pc, and we have equilibrium equation which is Pc is equals to twice Ps, which we can call it as equation of equilibrium, and these two equations in combination will give us the values of Pc and Ps. And once we know the value of Pc and Ps, we can compute the stresses in the copper bar and the steel wire, and thereby we can compute the final deformation that will be occurring in the whole assembly. So, similar to the one as we have done in case of evaluation of thermal stresses, we can evaluate the stress and the deformation in an assembly where we introduce pre-straining or the pre-stressing in the system. Well, after looking into these aspects, let us look into some examples related to these areas. Now, in the last lesson, I had solved one problem which is like this, that we have a rigid block of mass m which is supported by 3 rods, 2 copper rods and 1 steel rod, one central steel rod and 2 copper rods here and here. And of course, we had evaluated the stresses, it was asked to evaluate the largest value of m which we had evaluated from the criteria that the deformation of the copper bar is equals to the deformation of the steel bar, or delta C is equals to delta S, that is the final deformation which will happen in the system. And of course, the criteria of equation of equilibrium, that the mass is being supported by 3 bars. So, we had written down the equation of equilibrium, we had written down the equation of compatibility, and the compatibility criteria comes from the delta C, the deformation in the copper bar is equals to the deformation in the steel bar, and finally, they will be in the same length, or it will be a level surface. Well, we had solved that, we had evaluated the value of m. Now, subsequently, it is told that you need to determine the length of the 2 copper rods. We will have to find out the length of the 2 copper rods if it is different from 160, so that the stresses in all 3 reach their allowable limits simultaneously. Now, the point which is to be noted here, in the previous case, we had evaluated the value of m from the criteria that the deformation in the member is same, and thereby, since they are of different lengths, have different strains and correspondingly different stresses. Now, we like to find out that what should be the length of the copper rod, so that both steel and the copper rod reach to the limiting value of their stresses. So, the allowable stresses for these two values, for these two members are given for copper and steel, and they are 70 MPa and 140 MPa. Now, if we have to utilize the full stress of these two elements, then what will be the length L of this particular bar? Now, let us look into that. If we go into the full limiting stress, then what will be the value of the forces that they can undergo? Now, load that can be carried by the steel bar is equals to the sigma allowable multiplied by the cross sectional area A. Now, since the limiting stress is 140 MPa for steel bar and the cross sectional area is 1200 millimeter square, then the load that can be, maximum load that can be carried by the steel bar is equals to 168 kilonewton. Similarly, the maximum load that can be carried by the copper bar is equals to the allowable stress in the copper multiplied by the cross sectional area of the copper rod, which is equals to 70 MPa multiplied by the 900 is the cross sectional area. So, this is equals to 63 kilonewton. So, these are the values that the rods, 3 rods, the copper rod and the steel rod, that they can carry. So, if we go up to the limiting value of those 2 rods, then we can compute, still considering that the deformation of these members will be the same. From that particular criteria, we can find out that what length we need to achieve the full utilization of the 2 bars. So, from the compatibility criteria, that the deformation in the copper rods will be equals to the deformation in the steel rod, thereby it gives us that PC times LC by AC times EC, PL by AE. A is the cross sectional area of the copper rod, E is the modulus of elasticity. This is equals to P steel times L steel by cross sectional area of the steel rod times E of steel, and this is equals to, if we compute this comes as 63 into 10 to the power 3 so much of Newton times LC, this is what we will have to decide or you will have to determine, times A is 900 times 120 gigapascal times 10 to the power 3 megapascal. This is equals to 168 to 10 to the power 3 times length of the steel bar remains unaltered, which is 240 divided by 1200 into 200 gigapascal, which is 200 into 10 to the power 3. So, this gives us the value of LC, the length of the copper rod, should be equals to 288 millimeter. So, the length of the copper rod, if it is changed from earlier 160 millimeter to 280 millimeter, then both the rods or all three rods, the two copper rods and the steel rod, will reach to their limiting values or to their limiting stresses 140 MPa and 70 MPa simultaneously. So, for that we will have to make the length of the copper rods as 288 millimeter. Well, let us look into the second example. In fact, this is the example which we had set last time. This is the example which we had said last time. This is a truss which is undergoing change because of the change in the temperature. Now, all members of the steel truss have the same cross sectional area and the truss is stress free at 10 degree centigrade. Now, we will have to determine the stresses in the members at 90 degree centigrade. The coefficient of thermal expansion for steel is 11.7 into 10 to the power minus 6 per degree centigrade, and the value of E is 200 gigapascal. So, we need to evaluate the stresses in the member when the temperature rises to 90 degree. Now, here this system is not subjected to any forces as such, but is undergoing change in temperature, and obviously of course the supports are unyielding or do not have any effect because of the change in the temperature. So, now as we have done before, that we need to compute the equations of equilibrium, we need to write down the equation of compatibility, and then we write down the constitutive relationship between the stress and the strain, so that we can evaluate the unknown forces, as the stresses induced because of the change in temperature is indeterminate. Now, here if we look into that, because of the change in the temperature, the members will undergo elongation, because the temperature is rising from 10 to 90 degree centigrade. So, thereby as we know that delta is equals to alpha delta T times L. So, since this is length of this inclined member, let us call that A, B, C and D. Length of member AB and BD, they are 3 meters. So, the length of member BC, which is 3 sin 30 degree, length BC is equals to AB sin 30. So, this is equals to 1.5 meter. This is the length of BC. Now, if we take the free body diagram at this particular point at joint B, then we have 3 force components that are acting: force in BC, force in member BD and force in member BA. So, this is FBA, this is FBC and this is force BD. Now, if we take the summation of horizontal forces as equals to 0, then it will give us FBA is equals to FBD, and summation of vertical forces will 0 will give us that FBC plus FBA cos of this angle, which is 60 degree, FBA cos of 60 plus FBD cos 60 is equals to FBC. So, if we look into the equilibrium equation will give us FBA is equals to FBD and FBC plus twice or FBA cos 60 plus FBD cos 60, this is equals to 0. So, FBC, since BA and BD they are same, so this is twice of FBA and cos 60 as half. So, FBC plus FBA is equals to 0. So, thereby FBC is equals to minus FBA. Now, thereby it says that if because of the change in the temperature the central member is undergoing extension or there is a tensile force in the bar FBC, then FBA and FBD will be subjected to a compressive forces. So, the whole structural system having 3 bars will undergo expansion because of the temperature, which is equals to alpha delta T times L is the deformation because of temperature, and because of the forces that is getting generated because they are constrained, they are not free to move, they will have tensile and compressive forces for which there will be deformation, and if we equate that we will get the equation of compatibility. So, equation of compatibility in that sense is equals to, then if we say the expansion of the central bar as delta BC plus the force in the bar BC times L BC divided by A of the cross sectional area of the bar BC times E, since A and E are same we are writing as A and E. So, that is the deformation of the bar, that should be equals to the deformation of the bar. This is for the bar BC. Now, for bar BD or we have the deformation equals to delta BD or delta BA, which is again due to temperature, which is alpha times delta T times L, and for the force, for the compressive force we will have F BD or BA times L BD by AE. Now, if we look into the deformation configuration of the joint B, if we look into the deformation configuration of joint B, if we exaggerate that, let us say this is the original position of B, this undergoes deformation and comes to this particular point. Now, from here, so this was the original direction of the members and this is the deformed direction of the members, which are BD and BA. Now, this is the deformation that is being caused by member BC, which we have called delta BC, and if we drop a perpendicular here, now this is the length of the inclined member. Now, basically it should move in an arc which is in a circular form. Now, since the deformation is small, we are taking this as a straight one. So, if we drop a perpendicular here, this is the deformation which is being which is undergoing in the member, in the inclined member 1, and if we call this deformation as delta BD, now this angle is 60 degree in its original form. Since the deformation is small, we still call this angle as 60 degree. Hence, the delta BC cosine 60 is equals to delta BD. So, we can write delta BC cosine 60 degree is equals to delta BD, and the deformation which we have obtained in the member is alpha times delta T times length, which is 1.5 meter for this, plus the force in the member BC times length of the member BC divided by AE. This is equals to cos 60 is half, so twice of this, so 2 times, then we have alpha delta T times length of the member BC minus the force which we have, force in member BD, sorry, this is length BD. So, force into BD times length into BD by AE. Now, from this, since we know the relationship between FBC and FBD, so only unknown is the force FBC and all other parameters are known. So, we can compute the value of FBC and from which we can calculate the stress. So, once we know the value of FBC, so forces in the members FBC, FBD and FBA, they are known, and force divided by is the cross sectional area. Now, since the cross sectional area is the same, so that will give us the stresses in the member. Well, we have another example set for you, which is we have a compound bar wherein we have 3 materials, bronze, aluminum and steel, of length 800 millimeter, 500 millimeter and 400 millimeter, and they are combined together and put within the 2 fixed wall. Now, initially they are stress free. Now, we will have to find out the stress in each material on each part of this bar, of the compound bar, which is made out of bronze, aluminum and steel, when the temperature drops by 30 degree centigrade. So, initially from some temperature it drops by 30 degree centigrade. Considering that these walls do not deform, we will have to find out that how much stress this bar undergoes because of the drop in the temperature. Now, because of the drop in temperature, if we, the way we have analyzed before, if we compute the stresses, that means if we remove one of these rigid wall, then this bar will be free to expand or contract because of the change in the temperature. Now, since here temperature is reducing, is dropping down, so this bar will undergo contraction. So, let us say this is the position where this bar comes from its original form. So, this is the deformation delta. Now, what we need to do is that to bring this bar in position, we will have to apply a tensile pull in this, which we call as P. Now, this deformation when we calculate because of the change in the temperature, as we know the deformation is alpha times delta T times L, and over the length, whole length L, we have 3 parts, 800, 500 and 400. So, we can compute the values individually and calculate delta. So, after computing delta, you can find out the value of P and equate these two. The total strain is equals to the strain due to P. So, calculate this. Next time we are going to discuss on this particular problem. Well, we have another problem, that what stresses will be produced in the steel bolt and copper tube if we allow a quarter turn of the bolt. Pitch of the bolt is given as 3 millimeter and area of cross section is 600 millimeter square, and with this parameter you need to compute the value of this stress. Well, in summary, we can say that we have discussed the concept of strain in compound bars due to change in temperature. We have seen the concept of misfit, pre-strain and pre-stresses, and some examples to demonstrate the evaluation of stresses due to change in temperature and pre-straining. Now, some questions are set for you. What is meant by misfit and what are its consequences? What is the principle of double acting turnbuckle, and what is the pitch of a bolt and how is it related to the displacement of the nut? We will discuss these questions next time. Thank you.